Okay, good. So welcome everybody to the finale of Ronen's trilogy. Yeah.
Okay, thanks, Avi, for the introduction. And if you made it all the way so far, thank you, first of all. And today you'll get to finally hear the actual proof of Chen's bound. So all in all, we're interested in this quantity. We want the infimum over all such measures mu and sets t as above of this thing. Okay, this is our object of focus in this talk. And in the last talk, basically we spent the time constructing this guy, which is just an evolution of measures. So we had some, we started with this measure mu. There's a chat that cannot hear anything. So I think recently, yeah, because I fixed an issue. Should I? Wait. 2 minutes ago, it should be fine. It was a couple of minutes ago. Okay. Before I started, it's fine. Okay, good. Great. So what are we doing? We start with our measure mu, and we're constructing an evolution of measures mu sub t for every t positive, such that, so mu sub 0 is just going to be the original measure mu, and we're somehow going to evolve it in the space of measures, and we're going to evolve it via these equations. So we're going to define the evolution via the density ft of mu t with respect to mu. So we'll have this evolution of functions, which are just those densities, such that f of 0 is just 1 for all x. These things hold for every x, meaning mu 0 is just mu. And then this is the important equation. What does it say? So df of t, if you remember from last time, if you don't like stochastic differential equations, just think of the discretization. Just think of this as f at time d plus dt minus f at time t, and think of dwt. So wt is a Brownian motion. Think of it as just a Gaussian centered at 0 with variance dt times the identity. So what this equation really means is that when we go from time t to t plus dt, we take our density and we multiply it by a linear function with infinitesimal gradient going in a randomly chosen direction. And this choice of at here is the center of mass of mu t, is the unique choice that makes sure that all of those measures are still probability measures. Okay, so if a linear function equal to 0 at the center of mass integrates to 0. So if you remember, so great. So this is going to kind of go with us throughout the whole talk. And we're also, let me also remind you some basic properties of this, which we established. There weren't so many actually. So some basic properties of the process. So the first one, which you can immediately see from the equations, is that mu t is a Martingale, a measure valued Martingale, meaning that for every subset W, mu tw is a real valued Martingale. Okay, this is just because this equation only has a Martingale term in it. There is no drift term. So the second property is that that we saw, and for this, we actually needed to use Ito's formula. You remember we looked at log of f, and we did d log of f using Ito's formula. And what we concluded is that mu t has, okay, so the point is that at time 0, we don't know anything, but as we evolve this process of measures, we eventually end up with measures for which we do have good expansion. Okay, and the only thing we still have to control is that this guy doesn't go to 0. So, you know, the picture is like that. We start from the uniform measure on some convex set, and there's this set T here. And as we run the evolution, we end up with a measure that, I don't know, maybe it's centered around here or something. Okay, so it's not really a uniform measure on a subset, but you know, it's this thing times some Gaussian. This measure mu t is already concentrated, but it's not clear at all. It could be that mu t is either way over here or way over here, meaning that it doesn't even get to see the boundary of t, which is, you know, like saying this guy is close to 0. So we want to say that with a decent probability, this measure mu t is over here and not, you know, over here or over there. Okay, this is more or less where we stopped last time. And for this, let's look at the Martingale. So let's define MT. This we also did, but I'm going to do this calculation again because it's kind of important. Mu t to be mt to be mu t of t. So this guy is a Martingale, right? Or actually, maybe before I do this, let me go back for a second. We had this thing. What do we conclude from it? Okay, let me first conclude from 1 and 2 that mu of the boundary of t, which is what we want to bound in the end, is by property 1, the expectation of mu t of the boundary of t. And then we just take whatever's inside the expectation and we use this bound. So we just end up with the fact that this is at least, and this is true for every t, root t times the expectation of, let me write it like this, mt 1 minus mt, where mt is just this guy. So mt is just going to be defined as mu t of the set t. And this is a Martingale. So we have a Martingale, and all we have to do is say that it started out at the value 1/2, right? Because mu of t is 1/2. We want to say that it's not moving too fast to hit 0 or 1. Okay, that's all we have to do. So no, this I don't want to erase. Sorry. Did I do that? Should I move it back? Will it stop the noise? No. Okay, so if the people on the Zoom can't hear me because of the background noise, just say something. Okay, so we're looking at this Martingale. We want to say it's not moving. The dx I'm putting in, this dx is not the same d as here. You know, this is with respect to time, and this is a space differential. So those d's don't have exactly the same meaning. This is why I don't write here d mu t of x, but mu t of dx to kind of save the, so it won't be confusing. Okay? But if it's not clear anywhere, just ask. Okay. So so what is this? Let me write it as, the point is this only depends on one direction. It's the norm of this vector. Let's write it as the supremum over unit vectors theta of this guy. Just take x minus at and multiply it by theta and integrate with respect to mu t. Take the square of this. I didn't do anything, just the definition of the norm. And the point is that if I use Cauchy-Schwarz to put the square inside now, then this is, you know, at most the supremum over theta of the integral of over t x minus at theta square mu t dx. And, you know, I can just change t by all of Rn now. And it'll only be bigger.
Can you go back to the supremum over theta? How did you get?
The norm of the vector is the supremum of unit vectors of the scalar product. Some people call it duality, I think. Okay, so it's bounded by this guy, and what is this guy? This is by definition just the operator norm of the covariance matrix of mu t. Without a square.
So even that you decided to do this Martingale, is there any loss in the last sequence of equations? I mean, probably replacing t by Rn.
Next to not, I mean, well, here's the point. So if the convex set T is either very large, you should gain something, because in essence, what you see here should not be maybe much larger than the measure of T, right? If you integrate something on T, then, you know, if it had a Gaussian tail, it would be like root log of the size of T. So you can improve this, but for us, it's not going to matter at all. Since we kind of only care what happens when the size of T is close to 1/2, say between 1/4 and 3/4, that's fine. Great. So now if we connect these things together, maybe let me do just a small calculation here. So recall that I want a lower bound on this guy, the expectation of mt1 minus mt. What is mt1 minus mt? It's like, you know, m0 is just 1/2. I can write it as 1/4, which is 1/2 squared, minus mt minus 1/2 squared. I think it's the same thing here and here. So I just care, you know, how far from 1/2 this guy has wandered. And for this, we have Ito's formula that tells us that d of mt minus 1/2 squared is, well, it's dm, let's do it, let's just do Ito's formula. It's dmt minus 1/2, sorry, it's mt minus 1/2 as a proposition. So far, really, there isn't much going on. I mean, the calculations are really very simple, but we do end up with this kind of suggested scheme of how one would show expansion. So we ended up with this proposition for any t, if we have that the integral between 0 and capital T of the operator norm of the covariance of mu t dt is less than 1/8, for any t which is small enough such that this is small, then also this guy is small, because we just realized it's even smaller than the integral of the covariance. We have that mu of the boundary is at least root capital T. Okay, so all we have to do from now on is establish an upper bound for the covariance matrix. Okay? Good. And from now on, this will be like a more hard analysis of really trying to understand this, how this operator norm behaves. But it's what?
You didn't even do this calculation in your paper before Chen, right? This you didn't do even for your 2013.
So all of this still appeared in my 2000. But so great. So now let me actually, I think it's a good time to do a little bit of like scheme of what the rest of this lecture will look like, and I'll also, put the history of what happened where. So here's the picture right now. So in the end, we want a lower bound on expansion. Please tell me if I start erasing this. I don't want to erase this. In the end, we want to achieve a lower bound on expansion. This, as we just saw, is implied by an upper bound on the covariance matrix of mu t, operator norm. Okay, so we do this process. We start from an isotropic thing. We want to say that our measures don't immediately get completely skewed along the process. So this is what we just saw. How are we going to do this upper bound? Well, we have Ito calculus. So this is an expression that we can try to take derivative. All we can do is take derivatives with respect to time, really. So let's try to take the derivative of this with respect to time. If we look at the formula for stochastic localization, it basically tells us that derivatives with respect to time, every time I take a derivative of some quantity, I have a linear function that pops out. So the derivative of something involving second moments is going to, something that involves third moments is going to show up. Okay, this is all we can, this is like a moment generating process. Derivative with respect to time gives us higher and higher moments. Are we bounding the Hilbert-Schmidt, the operator? I didn't say anything. But some kind of upper bound on this will imply an upper bound on this, and this is going to imply an upper bound on this. Yes?
Can you just switch letters or something? Because we have T appears already 3 times with different things.
Tau. Yeah.
Ronen,
Yes.
since you were frozen for the last minute, can you repeat what is tau 3 of mu t?
Tau 3 of mu t is the third moment tensor of mu t. So it's just, I'm just hand waving here, but there is a covariance matrix, which is the second moment cumulant. This guy is like the third moment cumulant of the measure mu t. Something involving third moments, I'm going to define it later much more rigorously. But I mean, the whole point is when you differentiate this, when you differentiate second moments with respect to time, you get third moments. Okay? So some expression involving third moments. And now here's like the history of how things kind of happened. This picture was already like in my 2013 paper. Basically, you had these two implications, and somehow I didn't think, you know, so in some sense, there were already known bounds on third moments, and they involved something called a thin shell, which is kind of like a bound on fourth moments. So thin shell behavior basically involves the following thing. It's a bound on the variance when x is mu t distributed of the Euclidean norm of x. So it's called thin shell because it basically kind of tries to say that you have some convex body or low concave measure. You want to say that most of the mass is inside a very thin Euclidean shell. So you want to say that the variance of the Euclidean norm is large. This is something that involves fourth moments. And then you do some kind of Helder inequality to get third moments. And then you can go all the way here. So this was the situation in 2013. And then came Intatli and Santosh-Vempala and said, hey, there is a much better way to connect the pieces of the puzzle here. So they basically found the right way to do these two implications, even though in spirit they are the same, but they changed the analysis in a way that you don't need all of this mess, which is like very deep theorems, which kind of Boas-Clartak started, and then there were many evolutions. You can actually take a much simpler bound. In a sense, the easiest bound one could think on, so simple bound on this tau3 that you can derive without almost anything. And if those pieces are connected together, you do this, 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 and you end up here with n to the minus 1/4. Which also matches in the slicing problem, you know, the best bound we had, which to me it was really surprising because it's kind of like out of thin air. You start with a pretty dumb bound, and then you do all of this, and you end up with this n to the minus 1/4.
Just to clarify, lemma also improves the dependencies hidden by the arrow?
So they also, they kind of, yes, they improved the analysis in these arrows. Yes, essentially. They really like, in hindsight, they really simplified the analysis. They just found the right way to do the analysis, I would say. Even though, okay, like the formulas are like very similarly looking, but it just works better. Okay, so you don't need this anymore. And then like the simplest bound gives you this n to the minus 1/4. But then what they said is, hey, we started out with almost nothing and got n to the minus 1/4. The n minus 1/4 gives a better bound on this than what we started. We're convinced, since it also matches this n to the 1/4 bound in the slicing problem, maybe this is the end of the story. Maybe this is really what you have, and that's it. And now what Chen realized is that somehow if you join, so first of all, he found the right way to use this lower bound here, and he added another ingredient, which basically said, okay, if I have a universal lower bound on expansion, this gives me some bounds on those third moments, sure. But really, if t is big enough, then we also know that the measure is nicely behaving, because we know that we've added this convex potential to what we started out with. So if we combine this thing for small values of t and use the fact that you have strong low concavity for large t, then those two together are already enough to give some improvement when you do all of this circle. And then the bootstrap actually works all the way to n to the minus little o of 1. Okay, so this is what we're going to do. We've got all the way here. Now we're going to do like this arrow. And once we do this, the rest is actually, I mean, once you have Chen's ideas, it's actually not very technically involved. The most technical, like this thing, there is like some formulas you have to write, but like the rest is not so bad. Okay, any questions about this scheme? Yes.
So the stochastic process that we're doing is actually smoothing out the measure.
So it's really adding curvature to the Hessian. It's adding low convexity. I don't see, it's not smoothing out like the heat equation is smoothing out. If the measure was an indicator of something, you will still have a discontinuity. It's making the measure more well behaved in the sense that it adds, this convex potential.
But it won't kill the discontinuity.
No, you will still, I mean, the f of t is, if you had the discontinuity here, you're just multiplying by something smooth, so you're not killing it. You're not convolving, you're multiplying. It's smoothing things in the Fourier domain, if you want. Okay. So let me erase this, keep the proposition. Actually, it doesn't matter. Let's just. So our next goal is to calculate, we want to calculate d of the operator norm. Let's define, first of all, AT to be the covariance matrix of mu t. And we want to calculate how the operator norm of AT changes. And for this, so the operator norm is not a very nice function. It's not a smooth function of the entries. Ito's formula will be, I mean, it's not a very nice thing to use Ito's formula on this directly, on the operator norm. But let's first try to understand the behavior of the eigenvalues of AT. And for this, let's first try to understand the behavior of the entries of AT. So let's calculate d of AT. Okay? And for this calculation, what we're going to do is we're going to fix t, fix some t, and I want d of AT at this particular time t. And I claim that everything is both translation and rotation invariant. The stochastic localization, it's pretty easy to see it's translation invariant. It just moves things by the center of mass. So we might as well assume that at time t, the matrix AT is diagonal, and also the center of mass. This is the identity. We cannot dilate, we cannot, right? Like not all, it's not invariant under all linear transformations, just isometries. Okay, so we're going to assume this and then try to calculate d of AT. Okay, and I'm going to define. So now I'm really going to consider those third moment tensors. So let's define xi, not x, psi I to be a matrix, no, psi ij to be a vector, yes, defined like this. So it's the integral of x, xi, xj, mu t dx. So this is psi ij of t, but since we kind of fixed t, I'm going to allow myself to sometimes omit t. Yes, just the vector x. So this guy is a vector. And I'm going to also define so maybe, okay, maybe let's just do this. So I claim that dAt at coordinates I and j is just going to be equal. So this is just a straightforward calculation. We'll do it. It's just going to be psi ij dwt. So these third moment vectors are going to determine how the corresponding entries of the covariance matrix is changing, minus AT squared ij dt. So the entries of the covariance matrix, I claim that they are just Martingales, and the covariance matrix also shrinks as like the square of itself. Okay, so I mean, instead of this, you can just write, if you prefer without coordinates, dAt is just, and if I forget about the translation, it's like this. I'm not going to use this formula, but maybe you will prefer it better. So it's just the third moment tensor. I contract it with a vector. I get a matrix, and I also have this shrinkage. Okay. Why is this true? So I mean, this is just a straightforward calculation using this. Let's do it. So AT is just equal to this. Sorry, tensor power 2. Right? This is the definition of a covariance matrix. And now I'm going to do D to both of these sides. I'll just do it. I won't write the calculation. You'll just see that, okay, maybe instead of mu t, let me write here ftx mu of dx, which is the same as mu t.
Why isn't it just x minus AT to the tensor 2?
It's the same.
It's the same?
Law of total variance. The variance is like, you know, the second moment times minus the expectation squared. Okay. It's more convenient to write it like this. So when I do dAt, I first need to do d of this thing. What's d of this thing? I just do d of this thing inside. I know what d of ft is from here. So I just get, when I do d, this term pops out. It differentiate this. What is d of little at? So it's minus at tensor dAt minus dAt tensor at, right? I differentiate that this is the chain rule. D of at tensor at is like d here and then d here. But at is 0, so this is just 0. But then I have another term, which is, you know, the Ito term, d of, you know, the quadratic variation of at. And this, I think, you know, I feel like if I'm If I actually, it's an easy calculation, but I don't think it's going to teach us anything at all. So I'm not going to do it. In any case, this is only helping us. This is like a positive definite matrix. So, you know, who cares? It just makes our matrix smaller than what it was. I don't need it. I can just neglect it. Yeah. I'm pretty sure. Yeah, I think it's not an actual loss. Yeah, I don't think you could actually use it, but good question. There are other uses of stochastic localization where this thing really plays the most important role, but we're not going to get into them. So, okay, so we basically established exactly this, right? We have those third moments, which are just those guys, and that's it. We just have this formula. So let me erase this calculation. So this is what the entries behave as you differentiate with respect to time. And now if you have the differential of the entries, the eigenvalues are functions of the entries. They're not continuous or smooth functions of the entries, but they are as long as all the eigenvalues are distinct. So we're kind of going to sweep this a bit under the rug, even though it doesn't change anything. But the next thing we're going to do is write the eigenvalues as functions of the entries and do the Ito's formula there. So let's define lambda I of t, the eigenvalues of AT, let's say in decreasing order, even though it doesn't really matter, in some order that we can kind of keep track of what happens with these guys. And yeah, close to time. Yeah, very good point. Close to time zero, you start with the identity matrix. So it's not a smooth function, but for almost every t, it's a smooth function. So if you consider a continuous function, a nice function of the eigenvalues themselves, then everything will be okay. And in the end, our potential will just be the sum of the powers of these things. So really, you don't actually have to go through the eigenvalues, but I feel like this is the best way to give an intuition of what's going on. So, okay. So here's a general lemma about matrices.
You're saying worst contents can be done just by looking at the trace of the powers of AT and then just analyzing that.
Exactly. Just look at the trace of the powers, which is a direct function of the entries, and analyze that exactly as you're saying. But I feel like, you know, even though it's simpler like to do it rigorously, it's less insightful because, okay, we'll see in a bit. So just a very general lemma of, you know, variation. Then the gradient of the ith eigenvalue of A with respect to the entry is just, so I have a diagonal matrix, the eigenvalues are written on the diagonal. The gradient of this eigenvalue is just this guy, is just EII, the corresponding diagonal, right? If I change any other entries, including the off diagonals, it doesn't change this eigenvalue in first order. But the Hessian of the ith eigenvalue already does depend on what happens with the off diagonal entries. this is equal to the sum over all j different than I of the following thing. So there's a factor 2 here, and here there's EIJ. You know, this I just mean here the standard basis vectors corresponding to the entries over lambda j minus lambda I. So what is this Hessian saying? It's saying if I change this off-diagonal entry by epsilon, this creates a repulsion between those two eigenvalues corresponding to the row and the column. And the repulsion is quadratic. It doesn't matter if I add something to it or subtract. It was 0 in the first place, right? The matrix was diagonal. So it's a symmetric function, and it creates a repulsion, and the strength of the repulsion depends inversely on the distance between the eigenvalues. The closer they are, the more repulsion I get. And I guess if you saw some random matrices, this is not going to be very surprising to you. There is usually some kind of repulsion between the eigenvalues that really prevents them from getting too close to each other. So in the end, what we'll have for the eigenvalues is some diffusions coming from these terms, from what happens with the diagonals of AT, but the off-diagonals, which correspond to those third moments of distinct coordinates, are going to contribute to repulsion between eigenvalues. And well, recall that we want to keep the operator norm bounded, so repulsion is bad for us, right? If all the eigenvalues are doing independent diffusions, then we just look at the maximal one, and maybe we can use a union bound, blah, blah, blah. But if we have repulsion between eigenvalues, it kind of pushes the maximal one even further away. And it turns out that the diffusion is not going to matter so much for us. This is, by the way, where you get some polylogarithmic term from it, but it's not the crucial thing. The crucial thing is you kind of want to bound how large the repulsion is. Okay, and
but the repulsion gets smaller if let's say you want the maximal one. If it goes bigger, then the distance to the others is not the repulsion.
Sure. If you have this large bulk of eigenvalues, and then the maximal one is over here, then you have a large distance here. But it's first of all, those things it's not always clear how to analyze this. Maybe you still have something here a bit more sparse. I mean, it's not so clear how to do these things. And maybe let me mention that. So we're going to use a potential which is the most straightforward one you can think of, which is the sum of eigenvalues to some power. Intat and Santosh, in some follow-up paper of theirs, realized that if you use the so-called still TS potential with a more involved analysis, you can actually get much better things for a log Sobolev inequality. So there is definitely room for improvement of some things if you control these things in a clever way. But yeah, so now look, we have the two derivatives of eigenvalues with respect to the entries. And we have we know the formula for diffusion of the entries. So we just need to connect those things together. And what we get, so we just do Ito's formula on lambda I. And we know D of, the ijth entry. And if we just connect them together, we get the D lambda I of T is equal to psi I. So this is the diagonal guy corresponding to this, the diffusion of the diagonal guy dWt plus And then we need to, so we do Ito's formula. This is the chain rule. And now we have the Ito term. So we need to take the second derivative, which is this. And in the second derivative, I need to put here the quadratic variation of each one of these entries. What's the quadratic variation? Let's go back to this. It's just the size of this vector. So we just get plus, maybe let me write it here. It's going to, so it will stay with us. So d lambda I of t is just psi I dwt. This is the diffusion term plus sum j not equal to I. Avi, am I writing large enough?
There is no not equal.
If you see it, it means it's large enough. And here we have lambda j of t minus lambda I of t. And the diffusion, how strong the diffusion of the off-diagonal thing is, which is just the norm of this vector. dt. And the only thing I forgot is this guy, which is just, you know, if A is diagonal, it's just minus lambda I square dt. Okay? Again, I didn't do, I mean, there is no calculation hidden behind it. I just plugged this with this using Ito's formula. Okay? I mean, if you don't follow this exactly, I don't feel like you're missing a lot of intuition. What's important here is that you have some third moments that cause repulsion between the eigenvalues. You can see the repulsion here. And like, in the end, you want to control the operator node. Okay. So now, do you want to do a 5-minute break? I'm happy to. So I think let's just continue. If that's okay. Good. So now let's fix some number q. Yes.
Why don't we get the question of like Dyson Brownian?
So the question is, why don't we get the expression for Dyson Brownian motion here? I mean, it's a good observation. This kind of resembles Dyson Brownian motion in many senses, that you have this diffusion and you have this repulsion. It's just not exactly Dyson Brownian motion, because Dyson Brownian motion comes from a different, a different diffusion of the entries themselves, which results in a formula that looks a lot like this. Only, since all the entries have the same diffusion, you don't have this thing, you have something else. But this is really, this is very close to the actual. It's not the Dyson Brownian motion, but it's a Dyson Brownian motion.
You still have like perturbing your matrix using
exactly the same, yeah.
But usually I don't see the different, like the second order term.
I mean, the whole point is you don't know how large these guys are. This is going to be the whole, this is going to play the most important role here. But, the analysis of this is, it's kind of a feeling of deja vu if you've ever seen Dyson Brownian motion, sure. Okay, so fix some Q and define. Now let's look at the potential. ST is the sum of lambda I t to the Q over all I. Okay. And now let's calculate D of this potential. This is going to, I know it's kind of tiring, lots of applications of Ito's formula. This is going to be the most tiring. I'm even going to use my notes, like equation, but after this, I promise like everything will be much, I mean, there is not too much technicalities after this. So just so that I don't get anything wrong. So, let's just differentiate this using Guito's formula. What's the derivative of x to the q? It's q times x to the q minus 1. And then I have dx. So I get q sum over all I, lambda I, q to the q minus 1, d lambda I, plus the Ito term, second derivative, 1/2 q minus 1, sum lambda I t to the q minus 2, d the quadratic variation of lambda I. So what is this? I'm just going to plug what I have for d lambda I. So I get q sum lambda I t q minus 1, and then psi I dwt plus sum over j psi ij squared lambda I minus lambda j dt. Now I have minus this thing, right? But let me just not write it, and instead of equals, write here smaller equal. This is only helping me. There is a minus here, and the eigenvalues are positive. So let's just, because I don't have enough space here, let's do this. And then I have, and then I have plus, and I'm still missing the Martingale term that comes from, well, this guy. Here, there's a Martingale term. So I'm just going to write plus Martingale. Plus some Martingale term.
What do you mean by a Martingale term?
Actually, I already wrote, or sorry. I already wrote it. So sorry, I'm making, yeah, sorry. But I did, okay. I still didn't do this. You're right. So 1/2 q minus 1, and let's put here q squared because it's already less or equal, takes less space, sum I, and then I have, again, lambda I t. Let's continue here. Plus 1/2 q squared sum I lambda I t q minus 2, and then psi I squared dt. Good. Let me write it a bit differently now. So if you look at it closely, these guys are not too different from these guys in the sense that I can write, maybe just let me write it kind of again like this. 1/2 q sum ij psi ij squared lambda. So I'm just putting this sum outside, and then I have lambda I to the q minus 1 minus lambda j to the q minus 1 over lambda I minus lambda j Yes, and plus 1/2 q squared sum I lambda I q minus 2 psi I squared dt. Q will be large. It will be like log n plus some Martingale term. Okay. If you look closely at this thing, what comes to your mind? Maybe use Lagrange theorem, right? Look, this is lambda I to the q minus 2. This is like a Lagrange difference between two things with q minus 1. So it's like the derivative at some point. So it's like lambda I to q minus 2, but not somewhere between lambda I and lambda j. But this is an increasing function of lambda I. So all of this is at most lambda I to the q minus 2 at the larger of the two eigenvalues. So this is at most q squared times the sum I and j psi I j squared lambda I to the q minus 2 dt plus Martingale. Right? Once I used Lagrange theorem and monotonicity, then this term is already the same as this term. And then I get a very elegant expression. And you see that we started out with st, which is sum of lambda I to the power q, and we ended up with something which is very close to st itself, only instead of q, we have q minus 2, and we have those things, which we don't know what to do with them still. Okay, any questions so far? So now, lemma, where do I continue? Okay, let me erase this and just, I want to keep just the final conclusion that dst is at most. So we ended up with dst at most q squared sum over I psi ij, the norm square of those vectors, times lambda I t to the q minus 2. Good. And then we don't care about any of the other things. Plus Martingale. Great. So you see, we have st, and we have dst is almost like something times st. If we only had a bound on this, then we could bound dst in terms of st. And here's a lemma that I'm kind of, you should put it on my account. I'll return it an even stronger thing later. These guys are like third moments. You can use some Poincare inequality to bound third moments in terms of second moments in a very like straightforward way. And for a Poincare inequality, if we know expansion by Chigger's inequality, we have a Poincare inequality. So by doing something rather straightforward, you have that psi ij. There's also j here, sorry. There's a sum over j, so it's the, maybe let me, yeah, okay, it's fine. Lemma, the sum over j of psi ij, no, all j different than I. It doesn't matter, it's just a factor too.
The lambda I that is assigned to the psi ij should be the lambda.
There is a repulsion from both sides. So for every I, psi ij sum over j squared is bounded by 1 over the expansion squared, which is just whatever Poincare constant you get. Given, so this is not always true. It's only true as long as things are more or less isotropic. Remember, this thing only gives a bound for isotropic things, but my measure is not isotropic anymore. So this is true as long as the operator norm of AT is O of 1. So as long as this operator norm didn't explode, we just have a nice bound like this. Okay, but we're going to.
The bound you will have is what you get in each iteration of the cycle. Maybe you start with a skeleton or quarter. You apply this, you get a better bound, and then you switch them.
Yes. Yeah, definitely. This comes from the bootstrap.
This will give you as long as we go longer.
Exactly. In each iteration, you can go for a longer time. Exactly, because this thing is bigger. Yeah, exactly. Yeah, that's exactly right. This is true as long as this is O of 1. I'm going to like kind of swipe something under the rug. All the calculation we do to see for how long this remains true. So let's just assume it's true. It's pretty easy to assume it by introducing a stopping time, saying we just stop everything when this holds true. But I see that like I'm looking at the time and maybe let me, kind of some things just swipe under the rug. But essentially what you can write if you have this is that D, so I just plug this with this and I take expectations, and this guy is just monotone in lambda I. So what I get is that D, the expectation of ST, maybe let me write little st, or I don't know, G of t to be the expectation of ST minus or plus n. You'll see why. Then I claim that the derivative of G of t is the derivative of the expectation of ST. I just take the derivative there. It's at most Q squared sum over I and J, expectation psi I J squared lambda I T to the Q minus 2, right? I just plugged this, it killed the Martingale term because I took expectation. And then I use this inequality, and I mean, I just, this thing is at most lambda I T to the Q instead of Q minus 2, as long as lambda I is bigger than 1. So let's add 1 here. So this is at most Q squared over whatever expansion we have times ST plus N in expectation. So G prime is at most Q square over psi N times G. Great, I can solve this equation, and I get that for all, so if we define T1 to be just, just something that cancels this out. So just psi n squared over q squared, q to the, no, I just want to cancel out. I'm integrating with respect to time. So I just, there should be a square here also. Just, yeah, there was a square here. Times some small constant, okay, whatever. Let's not write the constant here. Then, yeah, then we just know that g of t1 is at most. So g of 0 is like 2n, because s of 0 is n, right? It's just the trace of the covariance matrix. So it's 2n, but then, I'm adding to x of this thing. So let's say it's less than 4n. And if we take q equal to log n, so now take q equal to log n, then we get the expectation of the operator norm is at most, I don't know, some constant, let's say 2, for all t at most t1. Right? Because the operator norm is at most this guy to the power 1 over q. Just because it's at most the trace. So the operator norm is at most the trace of the matrix to the q, and then take this to the power 1 over q, right? A up is at most the sum lambda I A q 1 over q. Because, this is definitely more than max lambda I. Okay. Okay, great. So what do we have so far? Remember the proposition that said that, if we can prove this for some time t, then we have a lower bound on expansion. And what we have now is seems like we're kind of chasing our own tail. We're saying, if we have expansion, then, we can just take t to be exactly the expansion. So it seems like we did nothing. It seems like we just showed an equivalence. Expansion implies through all this chain that you have expansion, right? But if you have expansion, you also have expansion on this side. And okay, you see, right? We closed the loop in a way that's not helping us at all. So this picture, kind of everything existed before Chen's paper. And then Chen came along and said, wait, you can actually do something better. You can actually go farther than this time t1. Because somehow, okay, so the situation now is, we know that up to time t1, the operator norm is bounded. But after time t1, we have no idea. It could be that things are really tame up to this time t1, and then they're exploding like crazy.
There is no cancellation in this process. T1 just by upper bound would be by the time, squared over.
Right.
But yeah, I'm just wondering if this cancellation in this process. So really that's the best you can do.
So the question is, hold on. So is there some cancellation in the sense that okay, what do you mean by cancellation?
You could go for longer if you didn't accumulate it exactly at this
yeah. Yes. This is what we're going to see. Yeah, so a priori, you don't have anything, but Chen comes and says, hold on, you can actually go for longer. Yeah, I'm not sure what you mean by cancellation.
Cancellation might be in a random walk.
Well, it's not going to be ideologically due to some cancellation like in a random. Okay, you will see what happens in it. I think it'll answer your question. Yeah. Okay, so this is the state of events, and then let's now see the main ingredient that Chen adds to this soup. So Chen, so the ideology behind what Chen adds is, in all of what we did, we didn't use the fact that as t progresses, we have better and better behavior of the measures mu t. We just started with some global assumption about expansion, but we also know that the measures mu t become more and more curved, and maybe there's a way to, you know, take advantage of that. And this is manifested in this lemma.
So basically, you get a better Poincare inequality than you had before.
Exactly. As time progresses, you have a better Poincare inequality, which is manifested in this lemma, which I put my notes somewhere, but it fell behind the board. I think I can.
You really want something exciting, pick up this headgun, which is lying there on the floor, and pick it up.
Wow. Okay. I mean, I probably won't need it, but it's, yeah, it looks like a lot of fun. Here it is. Wow. No, this is someone else's. No. Do you want to hear about harmonic analysis? This one? This one? Just here? Here it is. Yeah. Wow, amazing. There's lots of chalk here. If anyone wants, we can kind of pick it up later. I think. Yeah, I would. Yeah, the other one is stuck pretty badly. So let's hope this is the one I need. It's fine. I think I'll be fine. It's not exactly, but let me try. I don't really think I need the notes. So now let's good. So here's the lemma. The lemma is that for Q at least one, we have that the expectation of S and for T2 bigger than T1, the expectation of ST2 over ST1 is bounded by, okay, maybe let me say it like this. The expectation of this potential at time T2 conditioned on what we had at time T1 is bounded by whatever we had at time T1 times T2 over T1 Q here, and 2Q here.
Don't you want the 1 over Q? The 1 over Q?
Yeah, of course, you're right. Hold on. Yeah, I think this is actually, yeah. This already, the Q is already inside the definition of S. So this is, if I'm not mistaken, this is the lemma. Let me quickly.
Without taking the 1 over Q.
Okay. Yeah, something had to happen, but I think I'll be okay. I think this is it. Well, if it's not it, we will figure it out. Yes. Leo was right. Even though it's also true without this, but yeah. And we don't need to keep. It's enough to take just one cube. Good. So, I mean, the philosophy of this is, you know, if we had some a priori bound at time t1, we can keep moving, and well, it could explode, but it does not explode too fast.
Wait, T2 will be, I guess, at least twice T1. So this will be bigger than 1.
T2 will be like a big multiple of T1. Yeah. So this is the lemma, and let's see how to complete the proof using the lemma, and then we'll prove the lemma. Okay? So we're going to define, so T1 will be what we had before. So T1 was, if you recall, it was psi n squared over q, whatever a priori bound we have, q squared. And T2 will be beta times T1. No. This is, it's bad if it's small. So T1, no, it's like this. The expansion is like 1 over root n, and also T1 is very small. We're only going for a very short time, okay? And T2 is beta times T1, and we're going to optimize over beta, okay? And now let's see what the lemma gives. So remember the proposition that, so the proposition tells us that psi n squared is at least, so if we're going to choose beta so that the integral between 0 and T2 of the operator norm is at most 1 over 8. And if beta satisfies this, then we have that this is at least T2. Right? This was the proposition, which is equal to T1 times beta, which is, okay, let's just write what it is. Psi n squared over q squared times beta. And let's see what beta we can take. So this is, this holds. What is this? I can, well, let me. Now try to bound this. So the integral between 0 and T2 of AT operator norm dt is always bounded by just T2 times whatever the maximum is. And what is the maximum? It's, you know, I can just use the bound from above. So it's at most the expectation of ST1, 1 over Q, times T2 over T1, which is beta to the power Q. We still didn't choose beta or Q, okay? But I mean, I just used this bound from above here. And T2 is really beta times T1. Let's write it here. It's beta times psi n squared over Q squared. And okay, Q was log n. Sorry about the mess. Okay. So I'm just saying, you know, this is always going to be beta, and I took expectation over both sides. So I just have the expectation of this. And what is the expectation of this? Well, I know that at time t1, the operator norm is at most 2. So this is at most n to the power 1 over q. Right? It's just the sum of, you know, eigenvalues to the q I have, which is n times, it's at most n times the operator norm to the q to the power 1 over q. So I'm left with n to the power 1 over q, right?
That should be like 2 n to the power.
St is the sum of eigenvalues. St to the, yeah, it's just the sum of lambda I to the power q. And this is, if I take 1 over q here, this again is at least, right, the operator norm. Sorry, this is at most. So now this is at most at to the q. Lambda I is at most at times n, because I have a sum here, to the 1 over q. So I get n to the 1 over q times the operator norm, which I know is bounded by 2 at time t1. We already saw that. Okay, good. So yeah, and now, yes. So now we just combine these two equations. So we know that this. Okay, so what do we know? So yeah, what? Say again. Sorry. Yeah. The whole thing should be at most, right, 1 over 8, exactly. And this suggests that beta should be whatever you get. Beta should be, let's see, log n square over psi n squared, right? Beta I have here q plus 1 and over n to the 1 over q. No. It's not a constant. Q, so q was log n, but now I'm going to choose a new q. I use the potential. Okay, I'm glad you made this comment. I use the potential up to time t1. We got to time t1, we established that the operator norm is bounded, blah, blah, blah. Now I'm going to use a new potential with a new choice of q. Yeah. It was q1 and now it's q2. Yeah. So I think this is what you get, if I'm not mistaken. Okay. And if we choose this beta, then plugging everything together, we have that T2. Okay, so psi n square is at least T2, which is beta times T1. So it's log n squared over psi n squared n to the 1 over q. 1 over 1 plus q times psi n squared over log n. This is T1. This is beta times T1. Okay?
Q2 is going to be much less than Q1.
Exactly. So now I get an equation. This cancels out, but I still have psi n squared here, right? This was the first proposition saying if I can keep going until some time without things exploding, it gives me a lower bound on psi n squared. I mean, that was like the whole framework. Okay. So now if I arrange things, I basically, so now let's just, okay, should I mean, from this you already get what?
You can tell us what comes out.
Yeah, if you just solve this for psi n, you get n to the minus little o of 1. I mean, you just get psi. Now take q to be root log n rather than log n. And the point is n is going to be here 1 over q and another 1 over q. So with root log n, this exactly can, the whole, you just kill the whole dependence on n. You just get some dependence on log n. Okay, I think this is a convincing argument. Yeah.
So this happens just twice. You don't, I thought the sequence of times. It's
like so in Yuanzi's paper, he just does it again and again. But you know, you can just write an equation and solve it.
Okay.
So you know, you can iterate, but you don't need to. Yeah. Exactly. So that's the way he wrote it, because this is, you know, what the proof really he does. But in the end, it's just you have an equation that where this appears on both sides. So, you know, just solve the equation. And you see, if I take q is root log n, then I killed any polynomial dependence on the dimension. Definitely. Good. So we're happy, and all we want is the proof of the lemma. That's the only thing left. And like, I think I'll actually have enough time to do the whole proof. So there's, I mean, there is not, at least I'll try. So here's the, so for the proof of the lemma, we need the following intermediate lemma. So maybe this was lemma 1, this is lemma 2, which just says the following. Suppose, so this is just a lemma about measures that says, suppose mu is log concave centered, and its covariance is diagonal. Define our psi, our third moment things like this. And lambda I, the eigenvalues of the covariance. Then there's jk. Yeah, so psi I are matrices now, even though it doesn't matter. It's just, you know, different way to think of tensors. Then for all q at least 1, we have that the sum of lambda I to the q minus 2. Maybe let me just do psi I j and put here x, just to be consistent with the previous notation. It doesn't matter at all. This sum over I j and here psi I j squared, which is exactly, recall what we wanted to bound before, is at most kappa, which is the Poincare constant of mu times the sum of lambda I to the q. So if you look at this for a second, we already had, you remember the lemma that I said I still owe you, the proof of the lemma? We had a simpler lemma that said, if the measure is kind of isotropic, if these guys are not too large, then each one of these guys is just bounded by this corresponding guy. But now what Chen has managed to do is say, I can generalize this to the point that if my measure is already skewed and not very nice, I can still have something of that sort. So we can keep going. Okay, and the proof of this lemma is just a bunch of, so this is a Poincare. We're going to bound this. So actually, let me just immediately use Chigger's inequality because I don't have much time here. So by using Chigger, I just get this. Okay, and you know the point is even when the measure is skewed, I have some good bound on this.
What is the assumption here? The assumption is that there is no bounded assumption.
No assumption whatsoever. Just covariance matrix diagonal, which is for convenience of notation, really, because otherwise I could rotate all these things. Okay, so this, I mean, the proof of this lemma, it's just half a page, which I can follow line by line. I can't really tell you much. So we'll see if we'll do it. But I mean, once I have the proof of lemma 2, lemma 1 follows just almost immediately. So I mean, just recall that we had the equation. We knew that dst is at most, we had this long calculation. We ended up with dst is at most q squared sum over I and j, and then lambda I to the q minus 2, psi I j squared dt plus Martingale. Uh-huh. It's just you just need to apply Poincare in the right way, but it's easy. Yeah. And let me go back. I'm sorry, I was a bit hasty here. So you remember I wrote here, this was the Poincare constant, and I changed it to psi 1 over psi n squared. But I don't want to, the whole point was I don't want to use psi n squared. I want to use the fact that I have a better estimate for large times. So actually, this is going to be 1 over t. Sorry about that. So it's true with 1 over psi n squared, but it's also true with 1 over t because the expansion becomes better and better as so of course this is not true if I didn't assume anything about this. So let's assume here that d mu is e to the minus 1/2 t x squared minus some convex potential. So for any measure that looks like this, which is what we have at time t, we have an inequality like this. Okay.
You think we'll write the left-hand side of that inequality on the top board in terms of the matrix A and the C?
There's still you're saying not to look at eigenvalues, but like traces of blah, blah.
I'm curious what it looks like.
Yeah, I'm sure there is, but I don't have it, off the sleeve. So, okay, we're really almost done with the proof. So here's d of st is at most this guy we already saw. Let's plug in this bound, which exactly gives us that this is at most q squared times 1 over t times st itself plus Martingale. So before we had 1 over psi squared, and also this was only valid as long as we didn't completely skew our our covariance matrix. But now we have something that gets better with time. And like you see, d of st is at most 1 over t st. So d log of st is at most like 1 over t. And if we integrate, let's just this again, an ODE. So if we write g of t is the expected, just a log of the expectation of st. Then we add g prime of t is at most q squared over t, right? And like, this is just integrate this, you get that g of t2 is at most log of t2 over t1 to the power q g of t1. Yeah, so yeah, let's do capita. Yeah. That's it, right? Like now it's e to the log. I mean, so this is exactly what's written here, I think. Should be. What? T2 over T1 is like n. Yeah, it was 1 over psi n. It was some logs, forget the logs. 1 over psi n squared n to the 1 over q squared, where q is like root log n.
Yeah, so the second part will be a constant.
Ah, yeah, yeah.
You can go another.
Yeah. You can go another.
Go another factor, polynomial factor is, I mean, if you start from
Yes, exactly.
then you go another polynomial factor, but then at the expense of super polynomial.
Exactly. That's. You can go another polynomial factor, and the expansion improves super polynomial, right? Yeah. So you see this is exactly what's written here, right? When you like, yeah, it's log of this, but what g was a log, so we're fine. I have 5 more minutes to show you the proof of lemma 2. I guess, unless, I don't know, do you think people are, I mean, the proof is, yeah, so it's hard for me to say in words because it's like really a half page of like a weird Cauchy-Schwarz. And I mean, in the end, yeah, this is the only lemma that I really, the only thing I can do is just write. I mean, we still haven't seen how to use a Poincare inequality to give some inequality on moments. So, I guess it kind of makes sense to actually write the proof. So just for convenience, I'm going to write sigma I to be jk to be equal to sigma ijk. So, I mean, these were vectors. I'm going to define these matrices because anyway, we're summing over J. We're just looking like at Hilbert-Schmidt norms of those matrices. And yes, let's prove this lemma. So we care about this thing, which is just the trace of psi I squared. If I put the sum over J in here, it's just the trace of psi I squared. So the trace of psi I squared is the integral xi x transpose psi I x mu dx. I mean, there's one psi I that I just explicitly written, and the other psi I is in these guys, right? And then the very mysterious Cauchy-Schwarz, which I have no idea how Yuanzi thought of doing that, is you can just do, actually this Cauchy-Schwarz is not so mysterious. The integral of xi squared d mu times the square root of the variance, where x is mu distributed, of xt psi I x, x transpose psi I x. So I just took one of this xi outside. Okay. This is just the Hilbert-Schmidt, so just the sum over I and j, xi x I j. And this is equal. So what is this? This is just, you know, lambda I. So it's root lambda I times the root of the variance. Maybe let me write it like this. Everything is centered, so I can write it like this. Again, I didn't do anything. This is like this. And no, sorry. Hold on. No, it's not an equality. It's lesser equal. Just because, yeah, I just replaced the variance by a second moment. And this is, sorry. Yeah, I'm going too fast. So let me take, like this pass from here is important. Okay, it's the variance of a quadratic function with respect to my measure. Now I'm going to use the fact that my measure has a Poincare inequality. Okay, and I'm just going to replace this by the gradient square of this. So this is less or equal than the integral of the gradient square of this thing. So instead of x squared, I'm just going to have an x here. So this is at most whatever Poincare inequality I have, which was 1 over t, times square root. The 1 over t is also inside the square root, times the expectation of psi I times x norm square, which is exactly the gradient of this expression. Sorry. Okay. And this is just equal to root 1 over t. And well, you can just think about it as the trace of the covariance matrix of mu times psi I squared. The lambda I is, yeah, there is a lambda. Yeah, right. Okay. Okay, so we have these. You remember we kind of have to bound these guys, but not exactly. In the end, we want an upper bound on this. Sum lambda I to the q minus 2 times the trace of psi I squared. Right? Good. So this is at most sum lambda I to the q minus 2 times root lambda I 1 over t trace covariance mu psi I squared. This is exactly what we had above. And now this is at most 1 over root t. And now I'm going to do some weird Cauchy-Schwarz. So I claim that this is true. Yeah, I mean, I just took one lambda I from here to here and did Cauchy-Schwarz. And the point of this Cauchy-Schwarz is, sorry, not one lambda I. So I mean, I divided this to lambda I to the q over 2 and the rest, which is kind of weird. I've never seen something like this, but you know, this is the way you kind of get this thing again, which we want to make appear. Yeah, so this I think is, you know, a kind of a weird step. And this is at most.
There is a sum over I missing.
Sure. Here and also here. Yeah, there's two sums over I, right? And maybe so this thing is equal to, like, each summed here is equal to lambda I to the q minus 2 rather than q minus 3. I'm taking one lambda I outside of here, and then just I'm going to sum. This is a sum over I, but also j and k, psi I j k squared. So psi I j k squared. I didn't do anything, just this covariance has this lambda I in it. And then, with this, here nothing happens. And, and the point is, what is this? This is just equal, so let me just write, it's equal to this thing again, 1 over root t sum lambda I to the q 1/2. And then this thing is, I can just write it as lambda I to the q minus 2 times the trace of psi I. Trace psi I squared. Sorry for the mess. I mean, I just wrote like the definition of this. And the cool thing is that this thing appears both here and here. So we can just move it and cancel it out. And we just get the inequality that's like written wherever. I guess we don't have it anymore, but we get exactly what we wanted, that sum of lambda I q minus 2 trace psi I squared is at most, I guess, 1 over t sum lambda I to the q, which is exactly what we needed. So, you know, it's kind of, I mean, it's kind of a cool way to manage the fact that the covariance has become kind of like not nice and still get some bound on this thing, which I think several people, you know, tried related direction, but no one could do it. So so do we use that the covariance is diagonal? Everything here is rotational invariant. It's just a matter of you know, it's just used for more convenient notation. There is nothing, I mean, you could write all of these in a tensor-like way that, but it's just more convenient to work this way because you use Cauchy-Schwarz on these sums on eigenvalues. So you might as well do it, but it's not like a,
where you take the place of the covariance times c squared, and you took out some eigenvalues out of it.
Yeah, he was using it, but he said that you don't have to use it. It will just be more complicated.
Yeah. I mean, maybe, I guess, as Vijay asked, maybe there's actually a simpler way to write it without indices, right? It makes sense. Yeah, I don't know if, I actually think, so Yuanzi does write it a bit differently and kind of without indices. So yeah. So I hope everyone is like, kind of agrees that we did the whole proof. I mean, we did. It was kind of a mess at the end. Sorry about it. But if there are any questions, I'm very happy to answer. Yeah, I'm looking at the 5 people sitting here, but you know, maybe there's 2 more people in the Zoom, so you can also ask. Okay.